Welcome, happy Thursday. Let's get started. Maybe the first thing, since I didn't make a slide about the course calendar, I thought we would look at it quickly. Here we are on February 20th, and so we have today's instruction, next Tuesday, and then next Thursday, and the Tuesday after that, and then 2 weeks from today is the in-class midterm. Sorry, that was a horrible mistake to make. The in-class review, I'm sorry, midterm review. Sorry about that. That's like the worst slip-up you can make, and I just made it. I'll edit that out of the video. It's the in-class review in 2 weeks from today. The in-class midterm is then the following Tuesday, the 10th. And so we have yet to finalize exactly when we're going to do this. If we could try to reduce the volume of our private conversations, I think that would be helpful for the public good at this point. Thank you. We're going to release last year's midterm exam without answers, I think maybe on this Monday. I can't remember what we agreed to, but the Monday before the in-class review. So again, I misspoke earlier. 2 weeks from today is the in-class review during our regular class time. The following Tuesday on the 10th is the in-class midterm. And on this Monday, we will release last year's midterm, which will give you a very good idea into what this year's midterm will look like in broad strokes. Not specific ones, of course. We will ask different questions. We write a brand new exam each time, but it'll give you a general sense of what to expect. Questions about the course calendar? I know, based on my office hours experience, folks are working hard on Lab 4, which is due tomorrow by midnight. Lab 5, we're going to look at in class next Tuesday, and then it'll be due the next day, I think, unless there's severe pushback, and then we'll change it. I'll discuss with the GSIs. Then finally, there is a Lab 6 that will be due before the review or possibly on that Friday, depending on what the schedule looks like and how people are doing with it all. So some more labs and leading up to the midterm. Also some more new material that we'll be introducing too. So today we'll talk about global warming, a little bit of game theory, which is fair game, which is in here as well. Any questions about where we're headed? Okay, so before I have a few notes about lab number 4 that cropped up in office hours. Before we talk about that, I wanted to mention this. So about grade scope logistics, you need to select pages corresponding to each answer on the labs. And if you don't, grade scope makes the lives of the GSIs really hard because it's hard to find the answers if you don't mark this. So follow the prompts on Gradescope immediately after you upload your PDF. There's a link to a YouTube video that will walk you through this step if it sounds strange. So folks get free passes up until now, but Lab 4, which is due tomorrow, will need to be done in this way so that the GSIs can do their work without staying up to all hours of the night, which is a very tough thing sometimes. So starting with Lab 4, the GSI will not grade questions that you don't assign a page to. You have to assign a page. Finally, remember that you do get 2 labs off out of a total. There will be a total of 11 labs in this term. So that's a pretty decent number of free passes rather. Questions about this? Okay. So I think we'll leave any residual questions that may arise to Piazza and office hours. If there are residual questions, do please alert us. So I had a very nice time in office hours with some very, very smart students, and we were parsing through some somewhat confusing language that's in the end of Lab 4. And this part of it speaks to this question of when you start counting. So there are kind of 2 things that I think were a little unclear about our phrasing of question 6.5. So it's stated in the problem set, would harvest rates be higher in year 1? And I think that is better stated, would the harvest be higher in the 2nd year? So there are kind of 2 things happening there. One is that the harvest rate is the variable that you are controlling. So, you know, whatever you choose to say is sort of tautologically true if you state it this way. So I think it is better stated, would the harvest be higher? What you're trying to get you to think about is what happens if you deviate from this optimal maximum yield sustainable rate found in part 6.3. What happens if you deviate up or down on that in some particular year if you do something different? And there's a pretty clear answer there. So I think I've gotten this right. To be honest, I get confused myself when thinking about this because there are different time scales on each of these little graphs. So the year one means to us usually first year, but it's actually the second year if you start at year 0, which the time scale does. So do the best that you can and explain your answer. And again, these are graded on a check plus, check minus basis. And clearly getting more precision is important for the midterm. But in a midterm exam environment, of course, you can come and ask us a question, and if we've made some mistake with making things too ambiguous, we can put this up on the screen to let everybody know. So please don't stress out too much about the unfortunate ambiguities that we inject into the stuff that we write. I do it all the time. Most of us do. And it's just an accent, so we'll just move on. The other thing is that 6.6, and this is a mistake that I fully own myself, not having actually read this other work by Becker that's on the reading list in recent memory. So the question asks about a different Becker, not Gary Becker, who is referenced in David Lamb's work from 2011. It's the S. Becker reading. I don't even know. Is it Stan? Yeah, okay, so it's been a while. That's the case for many of us there. So if you're confused by it, read the Stan Becker reading on the reading list. Questions about Lab 4? I'm impressed you're all here. It is a beautiful spring day, and I take it to heart that you're here listening to me instead of out enjoying the beautiful spring weather. If you do choose to take a pass on the rest of lecture, that's fine. Just go ahead and try to leave in an orderly fashion. Okay, so what are we going to do today? We're going to look again at this harvest model which shows up on the lab, and there's a high probability it might show up in some form on the midterm exam. So this is an adaptation of the Malthusian model that actually has a harvesting rate attached also to the death curve. Then we're going to talk a little bit more about the tragedy of the commons. We'll talk about the negative externalities associated with growth in population and also with economic development. So there are kind of two big things happening with global warming, and maybe I'm beating a dead horse or belaboring the point here, but one is that having more humans on the globe means that they typically generate more carbon dioxide and other pollutants. But the other issue is that there's a relationship between the amount that a person would generate and that person's consumption per capita, if you like, or that person's consumption. It's not monotonic. There's some evidence that it actually might rise a ton as consumption for that person rises, and then maybe it trails off as that person's consumption keeps going. And we'll talk about that. That's called the environmental Kuznets curve, and it shows up in some of the data that we see. So there are kind of two big things. One is the level of development. The other is just the number of people. And both of these things, it turns out, are unfortunately sort of bad news for climate. And then that gets you into this whole other realm that William Nordhaus has done a fair amount of work in, and I confess is so, I don't know, meta in a way. It's just sort of beyond my ken a bit. He talks about the international political economy of how to grapple with this. Political systems that might actually help us address this massive problem of a huge externality associated with economic development, which is producing carbon and spilling it into the atmosphere. So that's this huge negative externality. Last week we discussed the positive externalities of population growth, which is in some sense just so darn much more fun to talk about because it's a positive story. That was Nobel laureate Paul Romer from last year talking about cities and Burning Man and the benefits of population and learning to understand that other people are on net a benefit in that sense. And the Nordhaus perspective is a much more sober, maybe dreary, I don't know. Is it dreary? It certainly is a sobering perspective to think about what one can say about the prospects for global warming and agreement to reduce greenhouse gas emissions. So we'll either agree or disagree. I phrased it that way. I think one could, I guess, disagree with what Nordhaus has to say, I guess. I'm not sure how, but I suppose one could. And I think the point I was trying to make is that you might agree or disagree with this. The ultimate challenge for economists, or for economics and for economists, for young people, for honestly the human race, you could say, the ultimate challenge. But why is it a challenge for economics? It's because economics has these important things to say about incentives and behavior and the difference between what is maybe optimal for a population and what is optimal for individuals when they're making choices. And then we'll talk about policies that might help fight climate change. Questions about where we're headed? So we talked about inequality several class meetings ago, and I know that based on the poll, that's what the plurality of the class felt was more important or the most pressing challenge. And of course, I mean, the big unfair thing there is that if I were to say, well, why don't you list the most important things? Those of you who said income inequality probably would have said, well, number 2 is climate change, you know, or something else, maybe number 3. Yeah, so fair enough, that's true. So let's talk about this Malthusian model, which shows up in Lab 4 and is in that nifty little shiny app that Professor Goldstein and others programmed. What does this look like? It's the Malthus model with some adaptation. So there's a harvest rate that sits on top of the death rate and pushes this death schedule up across the board by this, whatever this rate happens to be, little h. So you might ask yourself, what is the optimal little h that will maximize the total harvest, which is the product then of the population of fish and the harvest rate? Now, another thing that came up in office hours is that it's very important to realize that here this is a Malthusian system of a fish economy. So humans are doing the fishing and they are reaping the harvest, but the population is not of humans, it's of fish. The wage is a weird concept of food per fish. It's not a wage paid to fish because fish don't have money, of course. They have gills, not bills. So this is all about fish, and so the people are basically doing this part. So let's try. It's easy to get confused, and so if you're talking about a harvest, it has nothing to do with how many people there are and how much food that they can eat. So what is the optimal harvest rate then that will maximize the total take, and how would you figure that out? And it's actually a very challenging thing. This is a dynamic system, as you have seen. How do we know? There's a difference between the short run and the long run. Here in the long run, so this is a harvest rate that has pushed the augmented death curve all the way above the birth curve for as far as the eye can see here to the right. So that means ultimately, in the very long run, this population of fish is going to crater and become 0 because the deaths will always exceed births as far as the eye can see. But this is a dynamic system. In the short run, you will have fish. This is kind of like in the short run, we have an atmosphere with oxygen and not all carbon dioxide. In the short run, we have land. It's not all underwater. In the long run, things are a little bit less clear. And so if you were thinking about a version of this that might, reflect climate, and I guess what would you say here? You would have to say the population of like, I don't know, seawater temperature, something like that, right? You want to think a little bit about what it is you're modeling if you're thinking about global warming in a sense, and I can't do that on the fly, it's rather hard. There's a long run in this model, and it's determined by the intersection of these two curves, but there's a short run too. And so if there were humans who happened to stumble across these fish, and they, even if they knew there was a birth and a death curve, they might start harvesting at this rate h. Well, it would start wherever we are initially, before harvesting started, so before fishing. And here's an N star, and there's W star. And there would be some population of fish that would move slowly as the harvest rate increased from 0. So it doesn't happen overnight that you might overfish everything. It might be very clear that you would quickly be overfishing, but it's kind of hard to tell. Now abstract from this and realize, the real policy issues, of course, are not fishing in like a pond or a lake where things are a little bit more observable. It's about fishing in the oceans, where fish go all over the place. And fishers come from all over the place too. This is extraordinarily challenging to try to figure out, well, what is the optimal harvest rate when the population sizes are guesses. You can never actually take a census of the fish in the sea, right? There are ways of trying to get at it, but basically it's an unknown thing. It's even harder to do than to take a census of all the people. So this is a dynamic system. It's something that evolves over time, and it's really hard to get a handle on this. I guess that's another part to say then about the externality of fishing, and knowing what the optimal rate is, it's hard to know. Okay, so beyond this point then, if this is your H, you've obviously pushed the thing into unsustainability. That will reveal itself over time, but not immediately. On the other side of things, it's clear that if you had a harvest rate of 0, then there must be no harvest, because the harvest rate is 0. So that's, that's sustainable, but of course it doesn't maximize your harvest, the number of fish that you get. And so by this logic, then there's got to be a beginning and an ending point. So this looks a lot like a Kuznets curve. It's not really the same underlying logic that goes into it, but it's the same shape. It starts at 0, and if it hits 0 again, that means it must have come, hit some maximum, come back down. There's all the things you can say. I mean, it's possible that instead of this smooth thing, it could be whoop, doop-a-doop-a-doo, I'm up here and I'm down there. Now, those sorts of things happen. And if you go into a PhD program, you might care a lot about whether this thing is sort of monotonically rising and then falling, or what, if there's just one maximum or if there are several. And of course, that can be different. What's the maximum? Okay. One way of working through that is by using this really nifty app, which is requested of you for Lab 4, and many of you have done that. And another way is just by saying, well, let's suppose some numbers popped out of our model. And so these numbers are plausible. They're not necessarily the same as what you might get out of the Shiny app. So I'll mention that again in the future, but please don't assume that this is the same as the Shiny app, and thus the right answers for lab number 4. It may or may not be. So here's the Malthus model with these different rates of harvesting here, where we've left the original death curve here, and then these lighter lines sort of represent the shifting of the death curve with these different various rates of harvesting. And so the vertical distance here should be the same. It's a percentage point in each of these cases, because along here we've got this y-axis in terms of percent, and so each percentage point pushes you up. But of course, notice that because this thing is concave, the actual, if you like, as the crow flies, distance between these things gets bigger and bigger each time you go. There's a bigger bump to, it turns out this food per fish kind of thing as you're going. That's also true down here because of assumptions. So we've got this curvilinear thing, which you would get under fairly standard assumptions. So here are the same harvest rates ticking you off different populations that would persist in the long run. I think that's one of the hardest things to remember here, is that these little points are all long-run equilibria. It's not necessarily where the system would be in the short run. And I think that's a great advertisement for the Shiny app, which reveals that you can see a time plot of the thing, working itself out over time. And, it takes you to the long run eventually, but you might not be there initially. So on an exam, though, solving for stuff, typically we would focus on things that you actually can do, and that usually has to do then with these steady states or long-term equilibria. So this is what we've got with these numbers. So notice we're 2,000, 1,700, 1,400 are the same that are back here. So we're just plotting these things that we've just ticked off in this example of stuff. And what we're doing is we're taking the harvest rate on the left-hand side, which are kind of the, if you like, the heights of each of these in the previous slide. So if you think about the z values of each of these xy combinations, that's the harvest rates here. I guess it's also the vertical distance. And we're taking this times that, and that's kind of easy to eyeball. So 1% of 1,700 is the number 17. This is fairly easy to eyeball too. 2% is twice 14 without a couple of zeros, and so it's 28. And so that's what we're doing. And if you like just looking at the numbers, then you can eyeball what the optimal harvest rate is in this particular example. It's here at 4. Right? That's at least integer-wise. If we're stuck with 4% and 5% and 3% and not something in between, 36 is your person right there. It's your optimal. And if you plotted it then, it would look like this. So here I'm taking the harvest rate again from the previous slide. That's the first column, and I'm taking the third column here, and I'm plotting it. So it's the total harvest as a function of the harvest rate. And this is what we had plotted out earlier, given just some logic there, that because there's a 0 here and there's a 0 there, you must be pulling in something in the interim, and so that's what this thing might look like, and here this particular optimum happens to happen at 4%. Okay, so not necessarily the right answer to lab 4, so please use the Shiny app and assess whether that, we're in the right ballpark or there's a different answer. You might ask yourself, well, how does the fishing economy actually reach this optimal harvest rate? Isn't it so nice that we have access to the Shiny app, or I've drawn it out for you here? There it is. There's the optimum. How in the world would you actually end up there? Well, suppose we were talking about a lake or an ocean, something finite and patrollable, something that could be secured. So if somebody actually owned the lake, thus they also own all the fish in it, provided that they haven't, like sold the rights to the fish or something. One of the funniest things about it, so home ownership in the United Kingdom, sometimes there's a difference between owning the land and owning the structure on top of it, which just blew my mind when I heard that one. It's like, why would you ever not own the land under your house, but you own the house? Man, that was weird. And apparently it just happens. And I mean, in principle, you could do that sort of thing. You write a contract saying, well, okay, I'm going to sell the land. Well, all right, but what use is the land if the structure is already there? Anyway, that really was weird. So in theory, you could have sold off the rights to the fish, and people do that sort of thing, of course, all the time. You would think of that as an augmentation of this, that maybe there's somebody else. If you like, think of it as hiring a manager to actually do this for you. So you're the landowner, perhaps, or the lake owner in this case. If the thing is owned, then what you could say is, well, let's go ahead and I'm going to plot this out with the help of my ecologist and tell you all that actually 4% of the stock needs to be taken each period, and there you go. So it's 36. You could also sell 36 licenses to take one fish apiece. Somebody could buy more than one license, for example, if they wanted to fish more. Notice that it takes a decent amount of work, of course, on the part of the owner here. They have to figure out what this number is, the number of licenses. And so, that's why you might hire an ecologist to do this sort of thing for you, is to try to figure out what that number might actually be to be sustainable. And it's not easy to figure that one out, but once you do, then it's pretty clear that provided you could actually enforce this, that you could get it done. But suppose nobody owned a lake, how would fishers ever collectively take just 36 fish each period? And the problem is that each fisher has the dominant strategy of taking more fish. If nobody really knows this and there's no mechanism preventing this kind of behavior, then that's where we're going to be headed. Stepping back, if this is really the story and the harvest rate that's optimal is 4%, what if some fishers deviate and they take more? Well, it's pushing us to the right here, to a harvest rate that's higher and thus giving you less of a total harvest. And it's also behind the scenes, if you imagine deviating, let me put it back here on the graph, deviating from 4% up to 5%, what you're doing is pushing the population lower of fish. So that could keep happening. Now let's go back to this and think about what's occurring. Suppose the number of fishers is exactly the same. So one of those Weisenheimers has decided to fish more fish than is optimal. Well, now the problem is you're on this side of the curve, and it turns out that your take, if the number of fishers is the same, then the take per fisher, the harvest per fisher, is now smaller. So what will you do? You're going to fish more. You're going to do it before the other guy can. That's a real big problem in a situation like this, where it's a natural resource that has some sort of recreating capacity, in this case birth or spawning of more fish. But if you can't change that, and of course, the fact is that where I grew up in the Midwest, Minnesota's the land of 10,000 lakes, and fishing is a really big deal there. And so what happens? Well, governments actually stock lakes with fish because they know that overfishing happens because everybody's got an incentive to go out and get more fish. They also, of course, have licensing, and that licensing typically establishes a season of fishing, for example. In some cases, I think it might establish a number of items that you can take, but the question, of course, is, well, how do you determine what that is? And it's a rather complex ecological process. Okay. All right, so let's look at some game theory, and I hope I got this right. I'm a little bit rusty at this, not having taken game theory in about 25 years or so. We often look at what are called Punnett squares, which are used in a variety of scientific applications. That, for example, you could think about genetic contributions and dominant genes and things like that. It's kind of a nifty one. So we've got one agent that appears along the rows and another appears along the columns, and a dominant strategy is a choice that is universally better for the agent. Now, what I'm going to show you is a very straightforward, simple, very, simplistic look at this sort of thing. If you have a game that has one round and then you're done. And with fishing, as with many other aspects of life, of course, that's not true, right? You have many periods to kind of put up with each other if you're all fishing together. So things get more complicated there when future rewards depend on current and also past behavior. And so I've tried to illustrate that a little bit in having two different of these squares to kind of illustrate the deal. So here's going to be period, I'm going to call it period 1 rather than period 0. So the first period, suppose I think about my choices and I've got two rows of what I could do. I could either fish a sustainable amount, and so if we think about the max total harvest for two fishers in the lake, then you divide it, and so I've got 18 and you get 18 if I fish a sustainable amount and you also fish a sustainable amount. But suppose you overfish, and suppose, this could be any number you like, but it needs to be a number that's higher, obviously, to be overfishing. So suppose this person gets 25. Here's the reverse flip of that across the diagonal, right? That if I overfish but you fish a sustainable amount, then I get 25 and you get 18. And suppose both of us go for broke and we both fish 25, let's say. And this number is sort of pulled out of a hat. The 18 is half of our example of 36. Well, why would you ever choose fishing a sustainable amount? You always do better if you end up down there. Especially, and I guess I didn't make this point very well, I don't think here, but what's going to happen on the next slide? So this is the max sustainable harvest. If this happens, either here or there, any other outcome other than this, the problem is that the population of fish is smaller. And so here's period 2, and I should have updated this number, but I didn't. A sustainable amount, suppose in period 2, combined might be 20 fish rather than 36. So I need to change that. The point is that if you are pushing to the left, you've already, cast that die, so to speak. You've gotten down here, it reduces the population of fish, and so the problem is that the next period, you're going to find your fishing gets you less, provided the previous thing happened. So this is a dependent thing that, it requires this to have happened in the previous slide. That if people choose their dominant strategy, they get more, but the problem is they've pushed past the max sustainable, and therefore there's less fish that they can get the next period if they actually comply. So, would fishers just kind of mutually agree that, oh, well, we want to avoid this outcome? What does it depend on? The number of periods in which you're a fisher, trust, communication, knowledge. I mean, suppose you were thinking about this and you said to your other counterpart, look, you need to fish just 18. Don't take 25, because if you do, it's going to put us into a situation where we've got fewer fish. We've overfished. Suppose your counterpart says, well, that's fake news. I don't believe you. Why do you know? Are you some egghead? That's kind of the problem here. You have to believe the forecast of what this thing actually is, the peak. And it's pretty obvious today in our modern political economy that this is a problem. So that's the nature of the commons here. The sustainable fish population size depends on everybody's choices, current and also in the past. Your harvest depends mostly on your own current choice. So you have direct control over how much you fish, but you can't control the stock of fish, which depends on how much everybody else has fished. So suppose you choose to fish less, or you're doing the strategy here, which is not a dominant strategy, of fishing the optimal amount. So suppose back here, suppose you decide, well, I'm just going to fish 18 fish always. Well, what's preventing this from happening? And the answer is not much, unless the other fisher happens to be your relative, right? If you're all family, then at least you can, be a jerk to that person at Thanksgiving or something. You have some recourse. If it's just some other person, you usually don't, unless there's actually a law that says, well, you have to actually fish just 18 fish. Thank you very much. And we all know, right, that, all right, there might be a law about that sort of thing, but it's kind of like a speed limit. Are you actually going to drive 55 miles an hour on I-80? I guess it's 65, isn't it? Maybe, and you might not. And what would you base that choice on? Your perception of the number of flashing lights and police cars that you see around you. You might drive 5 or 10 miles an hour over the speed limit, something like that. So laws are not exactly the most ironclad things. So who is hurt by this? If you choose to fish less, it's you, by a lot compared to what you could get. And the flip side of it is, if other fishers are doing the overfishing, what does that imply about the future stock of fish? It's plummeting. So it's kind of a race to this prisoner's dilemma, really. A race. It's called a prisoner's dilemma because this is the worst outcome. And the problem is that it's your dominant strategy. It's also your friend's dominant strategy to go there. And the metaphor, of course, from game theory that many of you probably are fully aware of is that it's the prisoner's dilemma where if you both are accomplices in a crime, it's your dominant strategy to rat the other person out before he or she rats you out. Even though it would be best if you pull a Trump administration and everybody just sticks to the story and doesn't actually admit anything. I guess even that's not quite true, right? They've admitted everything and still haven't gotten away with it. So the tragedy of the commons happens when you've got these individual incentives that are not really compatible with sustainability. And it usually is associated with this problem with property rights. If somebody actually owned the pond where all the fishing was happening, that person could observe what's happening and price things in some way. They've got control over the lake, the pond. You can see as the thing gets bigger, it's obvious how hard it gets. When we're talking about a climate, I mean, that's just really tough. A global climate, who in the world owns that? I guess we all do, but that's a tough one. It's very hard to define that well. So all these require agreement or cooperation, and the famous language here by Hardin was the mutual coercion and mutually agreed upon. The coercion to do something that's not really in your own individual best interest, it's in the best interest of the system. And of course, to see that, the problem is you have to have some ecologist or somebody who is plausible and people believe and people don't just dismiss it as non-scientific or something. Probably a much cruder word. All right, so here I've got basically a trick question. We'll see how we do this. This is for discussion. This is a totally unfair question. What isn't a tragedy of the commons? Is it the jammed up westbound Bay Bridge? Is it global CO2 emissions? Is it fishing in the Atlantic Ocean? Is it the inability to see the stars on a clear night? Or is it answer E, trick question, all these are tragedies of the commons? Okay, so I'll close polling. And we'll have a discussion on 3, 2, 1. Close polling. Okay, so I think E is a great answer. I realize I phrased C a little strangely. All I said was fishing. So that's a tough one too. So I didn't write this question nearly as well as an exam question should be written. But when I wrote it, I actually thought, the thing is, fishing actually is a little different in this regard. It's somewhat maybe stars on a clear night, kind of. But the real thing that doesn't belong here is actually A. And why is that? So what's different about the Bay Bridge, the westbound Bay Bridge, versus the rest of these sorts of things? There's a toll. So there's a toll on the Bay Bridge. So then you might ask yourself, why is it jammed all the time? The toll's too low. It's too cheap a price. It's too low. So there actually is a price associated with that thing that is congested. So it then gets you into this sticky morass. So I really liked A as being a good answer here. And some folks kind of got my thinking, but I agree. E is a very good answer as well. Absolutely. If there's something that actually is priced, it just isn't priced accurately to actually remove the traffic jams, that's sort of on us, right? I mean, we've actually priced it. We've made it excludable. In some sense, the Bay Bridge is a classic public good in that it was built with government funds, I think. I think the Golden Gate might have been built with private funds. I can't remember. Some of these bridges actually were built with like bond issuances, and it depends who issues the bonds. I think the Bay Bridge for sure, though, was public bond issuance, and I think it was part of the Works project and all that stuff after the Great Depression. There is a price associated with it, but apparently we just are not willing to actually price the thing according to how it should be based on the congestion. And there actually, let me just say, I didn't make a slide on this, but as many of you know, I of course love Twitter. I love my Twitter. And there's some discussion about left-right issues of the time and global warming, and somebody was trying to dunk on Elizabeth Warren for not thinking that global warming was important or deciding that it was corruption that was the real problem with global warming and all that. And it got me to thinking about it, and the thread went down this rabbit hole that it usually does. One of the things, though, about pricing things efficiently to remove these jams on stuff, and so if you think about the solution to carbon dioxide emissions is a carbon tax, usually. That's what's suggested. What form, though, would a carbon tax take if we actually took this advice of trying to get our house in order? It would probably be a gas tax that's higher. And is that gas tax, is that a progressive or a regressive kind of thing, or does it not much vary with, the incidence doesn't much vary with income? A gas tax is strongly regressive. It tends to take the biggest bite out of incomes for those at the bottom. And so this is one reason why you'll not see a lot of unanimity on this question of whether we should have things like a carbon tax, because unless you've got some mechanism to refund the tax collections, let's say, to reduce driving and other things that produce carbon dioxide emissions by raising the price of doing it, so that would be a gas tax is the most obvious one. Unless you've got a way of actually giving the cash back to the people who have very little means who are affected by this a lot, then you've created this additional regressivity in the tax system, and that's a reason to be a little concerned. So there too, I mean, why is the Bay Bridge jammed up? It's because we don't have the stomach to raise the toll to like $30. That probably would do a decent job of putting a dent in it all. Incidentally, was anybody driving on Tuesday on 80? Apparently, so I think westbound 80 on Tuesday was completely closed at Ashby. And what happened in El Cerrito, all of the surface streets that were southbound were absolutely jammed with cars. Because everybody gets off and they're like, well, I've got to get to work, so I'm going to go through city streets. Probably some of them drove on MLK, like down all the way to the Maze and then across or something on 580. Oh my goodness, and there's no price associated with that. All that is more carbon in our neighborhoods when people do that. Not cool, but so we need some kind of mechanism to help people, not do that, and it's probably a beefier BART system, and that's not cheap. Okay, soapbox, right? When you have kids, suddenly you start thinking about this. We were thinking about, where to live, and I could not bring myself to consider buying a house, no matter what the price was, near 580 or 880. And I was, no, absolutely not. And of course there's a reduction in price of housing around these massive arteries like that. And the reason is emissions are not good for little lungs. You don't want to live there, especially if you have kids. All right, so let's talk about population, global warming, and all that. There are these things that you might think matter. Population times, and then affluence is the thing that so here's another A, unfortunately, just to confuse us all. Because of course sometimes technology is actually the A in the models that we've got, but it's got its T right here, and iPad just sounds like a political slogan, I guess, for whoever's named Pat. Either that or an Apple product for somebody named Pat, I guess. So impact is population times affluence, or you can think about it as the amount of consumption per person times the technology that's available to sort of distribute this in some cleaner way. So what is the effect of changing the population on the total climate impact? Well, you could just think about it as being, the first derivative of this. If affluence and technology were constant, you would just get affluence times technology. You think then that, so changing these things obviously could change the first derivative here. But the thing that gets sticky is that both of these probably change. And there are these indirect effects then. These indirect effects you can think about as a chain rule if you're taking the first derivative here. So Malthus would say, well, if you increase population, you might decrease affluence. Boserup might say you increase population, or this is the Paul Romer argument too. You actually improve technology. And then Simon Kuznets behind it all sees increasing affluence eventually improving technology as well, also as a reduction in pollution, which I guess is the technology thing, really. See, the thing about affluence is that you could also, with more affluence, if you like, sort of have the breathing room to consider clean behavior. Taking the time to actually, clean up after yourself and sort all your food and stuff into the compost bin versus the recycling and all that, right? That kind of thing, which is sort of a luxury good. You have to have the time to do that. And if you are struggling with very low means, I don't fault a lot of people, honestly, for doing that sort of thing. So here's a Kuznets curve. It's just a simple, inverted U-shaped kind of thing. And we'll talk about him a little bit more later, but Simon Kuznets is mostly known for inventing modern income accounting. Why we actually have measures of GDP over time. They've been much altered since he came up with them. It was also kind of interesting that you really wish we could have had these during or prior to the Great Depression. They were developed because of the Great Depression. We had no idea what in the world was going on until we found ourselves in a depression, and that stimulated Kuznets and other thinkers to come up with the system of national income accounts. Yes? Why does technology increase impact? Well, so impact's on the left-hand side, right? And why does technology increase impact? Well, I think it's kind of a pessimistic view, right? What were you going to say? It uses resources. Yeah, if you're not having cars, you're not using gas. If you're using horse and buggies, you just are dealing with the poop, I guess. I mean, I'm not sure I really agree with this, but this is a view that's there in ecology. And I think it's exactly what Leslie said, was that the more intense living with improved technology of modern life, you're using more. You're using electricity, all of you, and of course I am, and I mean, right, all this is stored electricity. We've got batteries to do it, but it's all electricity that ultimately comes from burning stuff, whether it's natural gas, hopefully, or it might be coal. So I guess that's the perspective here, and I would agree with that. But right, the problem, and I think that what you've hit on here is a really deep point, is that we usually tend to think of technology as being things that mitigate impact. Technology as being ways of doing things better with what we have. Whereas I think this view, and I agree that there's something to it here, that a more advanced, but then it sort of spills into affluence, really, doesn't it? Right? Doesn't the concept of affluence sort of include this question of, well, whether you have cars versus wagons? So it's a little bit murky, isn't it? We'll come back to this in the review session if we decided to write an exam question on it. Okay. I'm not an ecologist. Ecologists are smart people, and that's usually what I think they think of it in terms of that. And I don't think that way, and I don't have much to say about it. There's also then this environmental Kuznets curve, which is a little bit more of hand-waving. Well, stepping back, I mean, I guess this is a bit hand-wavy too. It's this point that arose in the Piketty and Size reading early on. They used it as sort of a straw man in some sense, an argument that you set out there to then knock down. Suppose you actually think this were to happen, that somehow inequality rises as markets develop. You could argue that the nature of capitalism and development of markets requires there to be some concentration of resources. And I suppose maybe, I don't know. So that's the argument. And then somehow, it's a luxury good then to have less inequality because everybody's sort of raised, all boats are raised at the same rising tide, that kind of thing. Questionable to begin with, and then this is also a bit questionable, but there is actually some data that suggests maybe this might be going on. This kind of thing that pollution might actually fall Now, one of the questions is, well, pollution in the level of pollution, or like the pollution per GDP, or some other thing, or pollution per capita or something. You might wonder what this actually is. But it's the same sort of thing. We're positing maybe some kind of relationship here, that there might be less pollution as you advance in terms of your wealth, you could think of it, or your means. And it's, it's attractive. Again, it's, clean environment. If you're struggling to get by and to feed your kids, I wouldn't be too surprised if maybe the clean environment took a back seat to that. If you have higher income and what you're more worried about is, making sure you watch the Oscars on time or whatever it is these days, that, paying attention to the environment seems more plausible as an actual good that you would invest in. And so I think that's underneath it all. There's sort of a mixed record in practice, and here, I'm playing fast and loose with what it is that we're measuring. A couple of things to say. So this is from one of William Nordhaus's publications. This is actually the CO2 to GDP ratio, so the carbon dioxide emissions as a share of GDP, which is a little funny because one's sort of dollars and one's kind of metric tons or whatever it is, something like that. But you can still calculate this, and of course you've got to figure out a way of measuring GDP across all these different countries that are shown. Here's China with a very interesting downward slope here. The other thing that's happening is that the scale is basically log. It's not an arithmetic thing where the distance is always kind of changing a bit. Here's a 10 percentage point, but 5% is getting bigger the lower you go. And so China has this rather interesting trend here that kind of makes one wonder a little bit about the reporting of the carbon dioxide emissions. I don't know, but I mentioned this to Professor Goldstein. We looked at it recently and said, well, maybe it's the transition from making steel products to making iPhones. Maybe when you make iPhones, there are less emissions involved, and maybe some of the raw materials production is happening elsewhere in the world, not so much in China, and that certainly could be true. It could be possibly in India. So here's a rather interesting trajectory with India, starting low, rising, maybe plateauing, maybe, and then coming down. India is a tremendously interesting country for reasons we'll get into next week. It's a great example of a country going through the demographic transition as it develops. And here, too, it seems to be actually acting out this environmental Kuznets curve in some way. So time will tell. This, of course, stops in, I guess, 2005. But here, at least, I guess the cause for some optimism is that there are downward trends globally, again, in terms of CO2 emissions per GDP, and underneath it all, of course, GDP is rising. So if in China they're managing to expand their GDP very rapidly, and the Chinese are, the question is, how do they do it? And presumably, it's if this is true, then they're doing it with less and less carbon dioxide emitted per dollar of GDP produced. So useful. And also there are these downward sloping trajectories in the developed regions. So in the United States and also West and Central Europe, which is kind of an interesting polyglot. Okay, so there are transitions that arise in the course here. One is this, in the long-term sense of the way that an economy uses energy. So from an organic economy or agrarian to a carbon economy or newly industrialized to a more low-carbon economy, we hope anyway, and that does seem to be shown back here, where our GDP is increasingly becoming, often people say lighter, so it's less heavy metal that we're producing, not in the musical sense, but in the actual ships and tractors and all that. We're also producing services, and so that helps reduce the carbon emissions per GDP in the United States. There also then is the demographic transition, and we'll talk about that next week. And there are political transitions, and I wish we had said more about this during the course of the class thus far. It arose in office hours earlier today that political transitions are really big deals when you think about the underlying causes of income inequality across countries. Why are some countries so rich and some countries so poor? A lot of it has to do, and you may laugh when I tell you this, of the high quality of government in the high-income countries such as our own. Go ahead and laugh. And then the low quality of government in very poor countries. That one's a little bit more plausible. I guess the problem of, I don't know, the last 4 years, the assault on the rule of law has really left me rather depressed, but I think we will rebound. All right, let's talk about emissions and population and some accounting gymnastics, which are kind of useful. And so that's what Professor Goldstein had drawn out of the Dyson reading as being kind of pivotal, and I would agree. So what's going on in this table is a look at the population in the developing world. That's this first row. They are the majority, and they will be, and you can notice here too, the developed world, so we're looking at two different time frames here. 1.1 billion in the developed world in 2000, not much changed in 2050. Now, our population in the United States is rising, but elsewhere in the the developed world, the rich nations, many of those countries are seeing population declines, it turns out. And the poster children are places like Japan, Italy, I think Spain, and possibly Greece. Reductions in population because of low fertility. So that's happening, and that then kept the forecast, at least at this time, stable, where here we're adding another 3 billion in the developing world. Now, the next two columns, again, look at something that's changing over time or not changing. And here are tons of carbon emitted per capita. And so the supposition in this table is that the number here stays at 2 for the developing world in both time periods. So 2 in 2000 and also 2 in 2050. Suppose it stays at 12, a much higher level, 6 times higher, but also does not change. And then looking at the number of billion tons of carbon that are emitted, then in 2000 you get a number like 23 with this. So we're taking 5 billion times 2, and that gives us 10, 1.1 times 12, and that gives us 13. We sum them up, it gives us 23. And then here we've got 16, which is the product of 8 and 2, and you can see me doing all this, and sort of walking through. There's 1.1 times 12, also 13, and thus 29. So an increase in carbon emissions is in this business as usual. And then he's got two other scenarios, an optimistic one. Let's start there first. So suppose we have an optimistic one where suppose somehow the developing world is still stuck at this lower level, which is probably not realistic, to be honest, and that's sort of the point of the next slide. Suppose in rich countries, this gets reduced by 40%. What would you see? Well, you would see a reduction in this from what it was. So this is now 23.5. In the previous slide, it was 29. It's still above the level in 2000. So a pretty drastic reduction in emissions doesn't really get you super far. And again, this is not in emissions per GDP, it's in the level of emissions. A 40% reduction is a darn big decrease. So even if you have this really big decrease in the developed world where we are rich and are enjoying it, but presumably at this point can start paying in terms of a better environment for, out of our richness, basically. Even if you did that, you wouldn't see a really big change. Now let's think about a realistic scenario here where rather than just treading water, well, I'm not even sure this is really technically realistic, but so we've still got our 40% reduction for developed countries, but now suppose realistically we think that in developing countries they've doubled their emissions, and this gets you, up there. Why? Well, there are a lot of people living in developing countries, and so this was the way it was put back in the late 90s. So I was working at the Council of Economic Advisors at the time. It was just chaired by Janet Yellen, who later went on to chair the Fed, and she stepped down when President Trump declined to renominate her in 2017 or 18 or something like that. And so she would chair these meetings at the Organization for Economic Cooperation and Development, the OECD in Paris, where climate change is a really big deal. And the Clinton administration at the time was, pretty big into, well, what can we do about this? Let's talk about cap and trade, which is another version of a carbon tax. Basically, if you like, the metaphor of the pond with the fish, it's issuing these fishing permits and then letting the market sort it out, letting polluters actually trade for these pollution permits. So what she said back then, which was not, of course, her original idea, she just pointed this out in a very nice and parsimonious way, which is kind of one of the magical things she always brought to everything. She said, why do we, as the rich inhabitants of rich nations, think that it's on developing countries to fix this problem? It certainly is the case that they have more and will have more people, but we have benefited so greatly from, and this is showing basically the output or the outcome of having high income per person. And why would we, so I'm saying this in a very non-parsimonious way, Why would we think that we deserve to have all this industrialization and benefits to our lives, basically, through improved living standards, and that developing countries don't deserve that? It's a pretty ridiculous thing. So when countries get together to talk about this issue of emissions and who ought to be reducing carbon emissions, you would imagine it's pretty clear that these 5 billion people might say to these 1.1, well, look, we haven't benefited from all this industrialization yet. So why don't you just get your house in order and we'll do it when the time is right for us? And then the problem is, well, okay, but temperatures are rising, and how do we think about that? It's a tough one. You can see why Janet Yellen was so very successful and I was not, because she put that much more succinctly than I just did. Developing countries have a right to develop. We did. Maybe that's a shorter way of saying it. So population growth puts upward pressure on things, but it's hard to imagine a global reduction in population. It's hard to imagine a great big increase in emissions that's really going to change the big picture story a ton. So now let's take a break and have another iClicker question. What's a Kuznets curve, qualitatively speaking? Starts low, rises, falls, and ends low. Starts high, falls, then rises and ends high. Or monotonic, or flat. Okay, so let's close polling in 3, 2, 1. Let's close polling. Okay, so just kind of make sure everybody's awake. The right answer is A, and there we go. Good job. So Kuznets curve is something that looks like an inverted U. Okay, here we go. This is more fun. I think the causality running from human CO2 emissions and global warming is fake news, not a very big deal, a pretty big deal, the biggest deal there is, or we are all going to die. Okay, so let's close polling and talk about it. 3, 2, 1. Close polling. Well, so there's no right answer here. Let's see what folks think. So the fake newsers are still a proportion. Tip of the hat there. We're all going to die. Pretty big deal. Biggest deal there is. So that's consistent, I think, with the earlier polling. Is it the biggest deal that there is? And I think our sense is, and actually it's not the biggest deal that there is. Yeah. An interesting question would be, suppose you had William Nordhaus in the room and you asked him, is this the biggest deal that there is? And I don't know, because he might actually say, you know what, our broken politics is the biggest deal that there is, because without unbroken politics, you can't actually solve global warming. He might say that. I don't know. I'm not William Nordhaus. Wish I were. He's a very smart guy. Okay. All right, so let's talk about some strategies for controlling carbon. You might think about it in this way, and so this is the basics of an economic analysis sort of thing. If you could quantify it in some sense, if you were consumption of stuff and benefits of weather, and of course you'd want to think about this occurring over many periods of time, and suppose you had some kind of full income where you're paying for your consumption and then also you're paying for the quality of your weather. In some sense, and you will face this as you graduate and decide where to live around the United States or around the globe, how much you want to pay for weather becomes a very salient topic, because housing prices actually vary, right, with the quality of the weather outside. So right now, my poor parents in the depths of February are living in Minnesota, and they are hating it. But they own their house outright. They had a very, relatively speaking to our house, a very cheap house, right? And so that's the thing. So I guess that's the way I think about it. You might then slap it on a pair of axes here, and put consumption of stuff, or maybe along the vertical, maybe climate here. And there'd be some kind of trade-off here represented by the prices, if in fact they were linear and didn't change. And you might find the traditional way of thinking about this, that there might be indifference curves indicating kind of people's preferences. And underneath it all, this kind of is the way that Nordhaus's model operates, and it's also the case that not everybody thinks this way. So we're accustomed to thinking about costs and benefits associated with actions, and then economists try very hard to measure everything that's salient that they can. They seek the optimum And they don't zero out costs. They try to equalize marginal costs and marginal benefit of action. And so that's going to mean some CO2 emissions and some temperature rise and some sea level rise, because if you were to reverse it all, there are large costs. And so maybe that's fairly obvious, but I think it's useful to restate it. And the other thing is that you might wonder whether economists really are able to measure everything correctly. And that's a very important point. You have to have confidence in what you're measuring and that it actually gets what you think is important. So you would be surprised how many things can actually be measured. So one of the more extreme versions of this actually is that we place a value on human life, and you might think of this in a wrongful death lawsuit or something, but you also, it turns out, should think of it in terms of the EPA, the Environmental Protection Agency, setting regulations about certain things and compensation for victims of environment. But also thinking about, suppose you want to think about the costs and benefits of air pollution domestically, and it has to do with how many early deaths you produce because of damage to lungs and things like that. And so it turns out economists actually can do this using the concept of willingness to pay to avoid mortality risk. And so it's maybe not exactly perfect because you never get to, there's no follow-up interview for a dead person. Oh, was it worth it? We don't know, but still, people face mortality all the time in various ways. Sometimes, of course, the sad thing is, every one of us faces it if we cross the street. It's just that we've learned to live with a very small probability of getting hit by a car, but it's still non-zero, right? It's still positive. Other people, so like my brother-in-law is a firefighter, and he needs to deal with this on a fairly regular basis, the probability that a fire would claim his life or injure him severely. And that's part of the reason why the compensation for firefighters is as high as it is, because you need to compensate people to accept that level of risk. So the DICE model that Nordhaus presents from is something that looks at human utility from consumption at the center of it all, and all of the models of economic growth do. And so, you might raise some questions about this, and I think this is, with complete validity, questioned in other circles, whether this actually gets it right. Are we pricing things like species non-extinction? Are we doing that right? Are we measuring it well? And I think there are questions, and hopefully knowing William Nordhaus and his team and how detailed they are, it's probably in an appendix in one of the reports somewhere. Getting that right is obviously helpful. Okay, so some strategies for controlling carbon. Countries deciding on their own, maybe, global agreements, climate clubs, and so this is the thing that shows up in the Nobel lecture. It also showed up several years ago in 2015 at the American Economic Association talk that he gave. And also there are a couple other strategies for all the propeller heads out there. There are other things out there, and we'll talk about them maybe briefly. The main thing, though, is this sort of approach. Carbon taxing, cap and trade, whatever you might want to call it. Those are kind of mathematically equivalent. So it's not as if we have a horrible track record with this. So it turns out what you should do is ask your parents, mom and dad, what about acid rain? And they will remember what that is. But most of us probably don't know what it is. And the reason is that American and Canadian and Mexican folks got together and figured out the problem with acid rain. It was sulfur oxides and nitrogen oxides, that's what SOx and NOx mean. And EPA and other groups managed to figure out a way of addressing this problem. A huge externality problem here of power plants, I think in large part, emitting these things, producing acid rain that would kill fish and do other horrible things. Now, part of the reason that worked, I think, was that it's not driving cars that was one of the root causes. A big problem with carbon dioxide is its auto emissions. It isn't completely, but a big part of it is. And so when you talk about a carbon tax, that's going to be incident on motorists, you and me, and a whole lot of people who are much, much less fortunate than you and I. And that's, I think, a big part of the reason why it's a political question. Maybe not a non-starter, but a problem. So this is a problem too with carbon dioxide, where the effect that we may experience is the one that's maybe caused by, say, Russia or the the effects that China experiences may be caused by other countries or vice versa, right? There's a big free rider problem. In the case of acid rain, it's a little bit more localized. Power plants producing all this junk that would then ruin stocks of fish in lakes in Canada, so it might have been across borders, but only one border. Not so much a big problem globally. With global agreements, and we don't have a ton of time, so I'm going to motor through this. The point of this slide is that here were a bunch. There's Paris, and of course the big story there is that we will have officially, the U.S. will officially pull out, I understand, the day after the 2020 election. So I don't know what happens if Trump loses that previous day. I don't know what happens if suddenly we're like, oh, never mind, the guy's gone, or at least he will be in January, so we're back in. It's the weirdest thing I ever heard. So apparently we're out of this now. But Nordhaus shows this. Here is the global CO2 emissions over time. And I don't think any of these decelerations line up with any of those agreements. So there are decelerations, and a lot of it had to do with recessions. That's what comes to mind here. There's a big one in the United States around this period where Ronald Reagan was elected. Here's another one up around 2000, and here's another one up around 2009 when the global economy sort of fell off a cliff. So I guess we have our answer, right? The curb CO2 emissions, we should all just have a great big recession that lasts forever, right? Yeah, I'm sure that will go over real well in the primary voting. Okay, climate clubs is something that Nordhaus mentions, and it turns out I didn't even remember this until I Googled it. This was in the slides that Professor Goldstein had created. I don't remember this happening. Apparently there was a U.S.-China agreement under Obama back in 2014, and nobody knows about it because, of course, it didn't work. Now, the modern version of this is really more speculative. It's like, well, could you figure out a way of creating a climate club that actually had some teeth, and how would you do it? And so Nordhaus, and actually I wish that this could make it into the zeitgeist, because what Nordhaus says is use tariffs. And if you've been paying attention over the last 3 years, tariffs are the favorite tool of a certain other T-word person who occupies a certain place of power in the globe. And so tariffs, right, that's what he says. He says, well, what you can do is have a club where if you pay your dues, namely you limit your emissions, then you're in good shape. And if you don't, the goods that you want to sell into that club are going to be levied a tariff. They're going to be taxed heavily. Of course, the problem is that the lover of tariffs is not a lover of the climate science, sadly. So here it is. There's a link to it if you're interested in watching it. It's a little bit less showmanship-y and more sort of science-y than the Paul Romer video. But I wanted to mention a few cool things. He talks about mathematics at minute 12:30. And he quotes his advisor, Paul Samuelson, who is thought of as sort of the parent of modern economics, and there might even be a textbook out there still by this person, and he was the second Nobel laureate ever in economics and the first American. Mathematics is necessary for you to understand and analyze complex phenomena. And of course, economists don't have a monopoly on math by any sense. Of course not. The math is used in all different sciences, probably also in certain arts as well. And so, Nordhaus talks about this. And also a shout out to Simon Kuznets, who actually was the third laureate then. So this is the same guy who came up with the GDP measures and the Kuznets curve and all that. Mathematics is a language. It's our future. We need to study many things, poetry, art as well, but math is really important. And then he says, and this is hilarious, he says, that's all it is. He shows you this. That's all it is. See, it's so simple. And he says it with a straight face. And, I don't know. I think that's fairly complex. I guess if you were to sit down and really think about what's here, if you had some help, it's pretty complex. But the point is that you're maximizing something, and then here's an integral sign, and it's a sum over many, many periods, subject to some constraint, right? That's always you're maximizing subject to a constraint, and that's what it means to look back in the picture back here. You're maximizing your utility in this sense. You're finding the highest curve subject to this constraint. And the math, of course, is that you're looking for the tangency point here. where you're getting the slope of this thing equal to the slope of this thing. And of course, what is the slope of that thing? Well, it's not just the ratio of prices. That only works for the black line. This thing is a derivative, and that, it turns out, then pops out of what this very simple math is. Some of you are like, yeah, it's simple. Okay, all right, but it is, I guess, if you know what this is. And if you don't, then it's actually kind of complicated. I wanted to say a few things that I thought were useful just to kind of connect to what we have been talking about. So a key part of this is it's an infinite, off into the future, infinite sum of human utility from consumption. That's what we're maximizing. Discounted. Oh, and I forgot the minus row, right? I'm sorry. There's a minus sign. Sorry about that. There's a minus sign here. So it doesn't grow forever. There should be a minus sign right there. And the rate of time discounting matters. And I'm kind of going fast here, but let me just tell you the punchline. Why am I showing you this busy slide? Is because this. You need to ask yourself, do we really care less about our children's lifetime well-being than our own? And that's kind of one of the salient punchlines in climate science and policy. How much do we care about our children and their children? And if you care a lot about it, you might want to take more action today. So Nordhaus's model does what the mainstream does. It's a good way to start. I should say, too, that this rate of time discounting is related to the real interest rate. It's not exactly the same thing, but it is related to it. And it's because saving is a choice. And so you might think about, figuring out a way to get this real interest rate, which is the rate of return on capital, close to the rate of time discounting, because the real interest rate is what you get in some sense by squirreling cash away. And the bottom line then is, well, probably what he does is a pretty good thing. It's a good baseline to do this, to set the discount rate to about 2% and see what the model tells us. And it's probably not good to set it either to 0. So if you set the discount rate to 0, then what you're saying is you're valuing your children's lifetime utility and their children's lifetime utility and their children's and their children's and their children's exactly the same as yours. And if you do that, it leads to this sort of paralysis decision of, well, you probably would choose not to be born yourself or something like that, something rather extreme. It's also probably good not to set this discount rate too high. And in any event, the other problem is that even if you do this, it gives you an answer, but it also rules out the problem of what's called fat tail uncertainty, which is, you could think of it as being a lack of knowledge about the true distribution of outcomes. We don't really know for sure exactly what's going to happen in the future and what the impacts are going to be, and that's important. So let me mention, just again for the propeller heads, because I love this stuff too. So there's abatement and reduction. That's one strategy he talks about, but then he also talks about these two things. He's a very interesting thing to say about this removal of carbon dioxide through planting trees. He says, well, there's removal of carbon dioxide through planting trees, but, well, I shouldn't say but. And then he goes on. So deeply unsatisfying to myself, but I'm not an expert about this, and it may well be a dimension that's worth looking into and thinking about. I think traditionally one of the problems is, well, okay, you have to find a space to plant the tree, and you have to plant a whole ton of them. And then the problem is, it's not as if the trees are there forever. If you ever, have to take down the tree, whether you're, because you're worried about forest fires and you have to remove some out, the problem is that the carbon all comes out of the trees. So it's not all that obvious that that's really a long-term solution, but it sounds like it's worth thinking about. This is the really fun propeller head one, which is management of solar radiation, for example, through injecting dust into the stratosphere. And there actually are people who think about this. It sounds kind of nuts, right? But the concept would be putting something between us and solar radiation so that carbon dioxide doesn't create global warming on the same scale anymore. But the challenge here is that we don't know much about this. We don't have a test Earth to actually do this with. And you never know what might happen with a policy like this. So only abatement is realistic. We've got 5 minutes left, so let's take a quick look at what he's talking about here. He's got different policies, different scenarios, and it's worth pointing out then that, and these are in the slides that are on the reading list, these different policies, here's business as usual, which on the next slide is going to be actual price. A cost-benefit optimum, which is what the economists would say might be a good scenario to look at, something that assesses the costs and the benefits. And then also, because they are usually discussed in policy circles, the limit temperature things. And so he will say that limiting temperature increase to 2 degrees Celsius, which is actually kind of a large rise, right? Because we're all used to Fahrenheit and Celsius is, these are bigger degrees than if it's in Celsius. It's actually pretty big. He says that 2% is actually, 2 degrees Celsius rather, is actually kind of a big problem on the previous slide. That kind of thing, 2 degrees Celsius, might cost 4% of our income over the next century or two. Now, 4% is a pretty big deal in policy circles. For you and me, 4% is not insignificant, but it may seem like it's less of a problem. But any government policy that proposes to levy a tax that does this kind of thing is going to raise some eyebrows big time. There are costs, especially with 2 degrees centigrade, and there are lower costs then. So here's the price of carbon. The actual price is, Nordau says, is $3 per ton of emissions. So it's not much. I guess that's the units. The optimal rate is more, it's 12 times that, right? 36 would get us to this optimal rate, which balances costs and benefits. So we don't have a ton of time. Let me see. Let me just, end up with this. Then I'll ask you this again. if we've changed your mind having talked about this. This is what Nordau says, and it's a very kind of sober scientist prescription. People should understand the gravity of global warming, and this involves intensive research and resisting false and tendentious reasoning. Tendentious, I had to look it up. It shares a root with tendency. So it means, you have a tendency to say a certain thing, and so your tendentious reasoning means that you've come up with it because you already have a story, basically, and you just want to reason your way through it. There are people who don't believe in global warming, human-caused global warming, and, that is what he would say is, well, sort of tendentious reasoning. Nations must raise the price of CO2 and other greenhouse gas emissions. It's an externality that is not priced. And he thinks it's the biggest challenge for economics. It's one of the biggest things that economists know about is the problem of negative externalities. Policies need to be global, not just national or local. And this gets into this point. It's like, well, where do you start with policy, right? Policy making. And so as we go into the primary season and the presidential election, I think there is something to be said that we might need to start here first. Start in the U.S. first. Vote in policymakers who actually believe in science. That might be a good first step. And then finally, a shout out to, I guess, the Paul Romer side of things, which is great. Rapid technological change, that's fantastic. So just for kicks, before you go, let's take this vote again and see if there's a substantial difference. I'll go ahead and just put up I always enjoy just showing the histogram actually changing. You can vote and decide as you go. All right, well, thank you very much.